Graphs of quadratic functions. Notice we skipped right over section 3 in this chapter. Chapter 9, we're just going from 2 to 4. Oh, I think I'm on the wrong starting place, aren't I? Let's get back here to the beginning. So we want to talk about our objectives with this lesson. We're going to use the distributive property. We're familiar with that one. We certainly know how to use the distributive property to multiply. If I have 3 and I've got x minus 1 here, I can distribute that, whoops, to everything inside the parentheses, giving me 3x minus 3. So we're going to use that here relative to quadratic functions. We'll see what that looks like in a minute. We're going to use the distributive property to factor expressions. Distributive property to factor. So if I had 3x minus 3, I could use the distributive property here to figure out how to factor that, couldn't I? I would see that I have a common monomial here, 3. When I divide 3x by 3, I get 1x. When I divide a negative 3 by a positive 3, I get negative 1. Use the distributive property to collect like terms. Well, that's an interesting one. If I had, well, let's wait. We'll find an example there. Write the inverse of a sum. The inverse of a sum. What is the inverse operation of a sum? Would be finding a difference. So we're going to figure out what that is. Simplify expressions using the distributive property. And all of this is going to help us with some equations that would otherwise be rather difficult for us to solve. They won't be when we are familiar with these activities. We know how to do them. Here's our 5-minute summary. Use the parent graph of an absolute value function. Now you'll remember that when I'm talking about a parent graph, I'm talking about the very simplest version. So parent graph, I'm always talking about the simplest version of that particular function. So when we were talking about a parabola, the very simplest quadratic, simplest version is y equals x squared. The simplest version of an absolute value so my function f of x is equal to, the very simplest one I could come up with would be right here. Just absolute value of x. My input is x, there it is, all by itself. Up here, if I were using functional notation, instead of y, I'd be, say, function f with an input of x. Very simplest one right there. Okay, so what would this one look like? And please notice we have a negative here. What does that do? When I have this, I'm going to go back to the parabola because I assume that this is the one we are most familiar with. It's one we've done the most work with. But if I had y equals negative x squared, that graph would open downward, wouldn't it? If I were to graph this, I'm going to get a V shape with, please notice, my vertex at 0, 0. Perfectly symmetrical. My line of symmetry is right here, going right through the vertex. So, if instead of having function f of x is equal to absolute value, I say it's -1 times the absolute value of x, it's going to turn the whole thing upside down. And I've already graphed this for us. Still, the vertex is in the same place, isn't it? Notice that? We still got our vertex at 0, 0. What happened? It just flipped from, and where did it flip around? Right around the x-axis. So if you pictured that, oh, having trouble, sorry about that. If you pictured this on a hinge, it just flipped around, went down instead of going up. Well, here's a more interesting one perhaps. This one is negative. So I know that my parent, let me just do a little dotted version of it. My parent graph, when I flip it, of course we know that the parent was right here, but when I flip it to make it negative, it's going to be like this. That's not the whole story though, is it? Because what else is happening here? Instead of having a multiplier of 1 on it, it has a multiplier of 2 on it. So it's going to have a much steeper slope on these lines. In fact, why don't I grab the graph I've prepared right now. This is how much steeper it's going to be, and let me prove that to you. It's actually twice as steep. How can we see that it's twice as steep? Well, maybe we can see that with a few points. I don't know that I'm going to even use this chart over here, but the points I might go to are here. If I had taken the parent and just flipped it upside down, I would have these 2 points that are at two. Oh, I will put them in. At 2 and -2, right? And at -2 and -2. This certainly looks like, what do we call this? An even function. It doesn't matter whether I put in a negative or a positive. It's still going to give me the same output. Okay, and for my parent graph, I'm only down 2, but for my one that's being multiplied by -2, it's right down here, isn't it? So it's not -2, it's twice that much, which is -4. It's not -2, It's twice that much. It's -4. So this too has been very influential. Has made my graph much steeper. It's declining much more rapidly than it would have back here. One more thing we want to look at, and that's the line of symmetry. You may sense I'm being very, I'm having some troubles that you shouldn't even have to know about. Okay, let's look at the line of symmetry. We knew for this one it's right here. It goes right through the vertex. The line of symmetry is right here. Oh, let's talk about the vertex. On this one, where is the vertex? It's right here. It's the same as it was over here, and that's at 0, 0. Maybe I'll have a little bit better luck with this one. I hope so. We've got the parent graph of a quadratic function. Now, I really want you to memorize this one, to know it inside out. The vertex for this one is going to be right here, 0. When I put a 0 in here, 0 squared is 0, so I'm getting a 0 out. That's going to be my vertex right there. My line of symmetry is going to pass right through the vertex. Right there. I'll bring it down a little bit so we can see it better. And what are some other points I might put in? Well, let's go -1, -2, -3. Okay. -1, -2, -3. And we'll go +1, 2, and 3. All right. So if I put in a +1 and square it, what do I get out? So let's graph that point. Please notice I've got a 2 by 2 grid here. So, oh my gosh. Let me go back a moment. Oh, good. I was thinking, did I have a 2 by 2 grid here and talk about it like it was a 1 by 1? No, it was a 1 by 1. Okay, and if I put a 2 in and square it, I will have 4 out. So 2 in, 4 out. If I put a 3 in and square it, I will have 9. So I'm putting 3 in and I get 9 out. If I put a -1 in and square it, I will get 1 out. Okay, -1 in and +1 out. -2 in, +4 out. -3 in, +9 out. Now you're probably thinking I didn't have to go through all of that. We know we've got a line of symmetry. Whatever I have on this side of a line of symmetry is going to be beautifully matched because of the symmetrical nature right over here. So I really only needed to do these 3 points and then say, okay, on the negative they're going to be exactly the same points for my vertical. What kind of a function is this? This is an even function. Regardless of whether I put in a negative 3 or a positive 3, I'm getting the same thing out, a 9, for example. So now let's try putting a negative on this. As soon as I go negative with this, instead of having my parent graph with its vertex at 0, 0 and opening up, I'm going to have still my vertex right here, and I'm going to have my parent graph turned upside down. So now when I put in a 1, it becomes a negative 1. This, well, I should make a note of what I'm doing here. I'm doing y equals negative x squared. In a moment, I'll do this one, which is y equals negative 2 times x squared. When I put a 2 into this, I'll get a negative 4 out. If I put a negative 2 in, I get a negative 4 out. If I put a 3 in, I'll get a negative 9 out, so I'm way down here. And I'll have the matching dot over here. So this is with a multiplier on it of just 1. It's negative, and my multiplier is 1. What I'm really trying to graph, however, has a multiplier of 2 on it. The vertex is going to be at 0, 0. If I put a 0 in here, my output is a 0. If I put, well, let's try 1, 2, and 3. Oh, what am I doing? Don't do it there. I want to put those as inputs. Just a moment. So input 0 gives me an output of 0. And I'm going to try 1, 2, and 3 as inputs. I'm also going to try a negative 1, a negative 2, and a negative 3 as inputs. And now we're going to do this one. This is the one we really want to do. Oh, maybe I should be changing color so I don't confuse you. Got blue here. So I put a 0 in, and I get a 0 out. Here we go, right there. I put a 1 in. What happens then? 1 squared is 1 times a negative 2. Ooh, I get a negative 2 out. So positive 1 in, negative 2 out. I put a positive 2 in. 2 squared is 4 times a negative 2, negative 8. So 2 in and negative 8 out. If I put a 3 in, 3 squared is 9 times a negative 2 gives me negative 18. I'm off the chart. Now I know that it's still symmetrical, that my line of symmetry is going to go right through the vertex, right here. And that tells me actually quite a bit about the points on the other side of the line of symmetry. They're going to be matched. So I put a negative 1 in. 1 squares to a positive 1 times a negative 2. And I get a negative 2 out. Put in, let me write it. So I got a negative 2 out. I put in a negative 2 here. I square it. It becomes a positive 4 times negative 2. I get a negative 8 out. Whoops. Right there. So let me draw this the best I can. It's not too too good. I have a hard time with these electronic pens anyway. You'll notice that it is a bit slimmer. It's going down more rapidly than its green counterpart, this one here. I'll try to show what that would look like. That's a little wider. So when I start putting a multiplier that's greater than 1 here, my parabola gets narrower and narrower. If I had a really big multiplier on it, it would get really skinny. So that might make you think, well, what if I put something less than 1 on it? What would happen? Well, I'll tell you right now, it'll get wider. So if it's a multiplier that is greater than 1, it gets skinny. And if it's a multiplier that's less than 1, it gets fat or broad, narrow. Okay. This is what I've been waiting for. We see something quite different going on here, don't we? Instead of x being squared, I'm squaring x minus 3. This one, we're definitely going to use our t-chart. Where in the world is the vertex? Well, we can try some numbers here. Suppose I put a 3 in here. And I get bigger and bigger and bigger. And then I'll go smaller here, 2, 1, 0. Now, I'm thinking my vertex is going to be here. You don't even have to know that yet. We'll just do a few points. When I put a 3 in, what do I end up with here? Yes. Okay, so putting a 3 in, I have a 0. Three in, 0 out. If I put a 2 in, what happens here? I have a -1 and I square it. I get a 1 out, right? So if I put 2 in, I get a 1 out. If I put a 1 in, then I'll have 1 minus 3, or -2 squared. Put a 1 in, I'm going to get a 4 out. I put a 1 in, I get a 4 out. If I put a 0 in, I've got -3 squared, so that would be a 9. 0 is going to be 9. I have my axis of symmetry. I think my vertex is going to be there. How am I going to know whether that's my vertex or not? Well, now I'm going to try this point here, a 4. If I put a 4 in up here, what am I going to get out? One squared. That's right, so it would be a 1. And if I put a 5 in, what happens? I end up with 2 squared, I get a 4 out. So 5 in, positive 4 out. I put a 6 in, subtract 3, I have a 3 squared, I get a 9 out. So 6 in, 9 out. So what have I got here? I've got a familiar looking parabola, at least if I were drawing it right. Familiar looking parabola. Oops. Let me undo that. I should make that just a little stronger. And we'll draw it again because I accidentally got rid of my line. There. So I've got my parabola. I want to show you something about this. I'm going to group all that together so that I can move it around a little bit. Group. So we just did this function. Look at this. If I move it over here, what does that look like? Let's go back. It's exactly like the parent graph. So the only difference between this graph and the parent graph is where the line of symmetry is. Please notice what the difference is between them. With the parent graph, we would have been here for our vertex, and we're at 3. Isn't that interesting? It's exactly 3 up here. What happens is whatever this number is, x minus h, we're going to call it. H is how far over you are going to move horizontally. We're going to talk a lot more about this in the future. Find the vertex and draw the graph of this. Okay, find the vertex. Find the vertex. Well, I could do it with a T-chart. Want to try that? All right, so we've got x here and y here, and we're going to try some values. We'll do 0, -1, -2, -3, and hope that that's going to be giving us a pretty good idea. Let's try 0. When I put 0 in here, this term zeros, this term zeros, and I end up with a 5 here. When I put a 1 in, what happens? I get 1 squared, or 1, so I've got -1 plus 4 times 1, which is 4. -1 and 4 is 3, plus 5 is 8. So when I put a 1 in, I get an 8 out. When I put a 2 in, I'm going to have 2 squared, or 4, and I'm going to subtract that. Subtract 4 from 2 times 4. I better write that down. So I'm subtracting 4, and I'm adding 2 times 4. I'm adding 5. So I've got positive 13, and -4, so that's a 9. And let's try 3. When I put a 3 in here and square it, I get a 9. and there's a negative in front of it. So negative 9. 4 times 3, so that's plus 12, plus 5. So this time I've got a positive 17, 5. I've got a positive 17 and negative 9. That's 8. You notice something happening here? I think this must be our vertex. Do you have the same thought I have? Well, first of all, we know because this is negative on our x squared term that we're dealing with a parabola that's going downward. We didn't know where our vertex was. But now this looks like I've reached my high point, which is at 2, 9, and I'm starting to go down again. So I might not even be interested in these values up here. Forget these, I don't care about them. I'm going to try the next one higher. If I put a 4 in and square it, I get 16, and then multiply it by a negative 1. 4 times 4, so that's a plus 16. Plus 5. This ends up to be 5. Sure enough, this is symmetrical. See that? Dropping to 8, dropping to, from 9, dropping to 8, dropping to 5, dropping to 8, dropping to 5. So I found my vertex. It's at 2 in. I'm going to make this a 2 by 2, by the way. I should mark it. We should always mark our scale. So 2 in, 9 out. I'm going to keep going here. 3 in, 8 out. 4 in, 5 out. And we know this is going to be the line of symmetry right down through the vertex. So I really don't even have to look at my chart to know that these points are there. So when I do this graph, it's looking like this. Find the vertex. I had to look for the point which became my high point, and then it started to drop off on either side. Wow, that's really neat. And that's the end, as it rightly should, after 33 minutes. Sorry, I've caused a lot of delay in this one. Try to get better with my electronic pen. See you in class. For those of you who are curious, and for those of you who are interested in a little bit more, I want to show you something else we could do here to find the vertex. Let me just erase the work we've done. I'll leave the scale there. And suppose we wanted to figure this out without having to use a t-chart. Some of you already know how to do this. There is a little formula we can use. I'm not going to employ that. If you're interested in it, you can look it up. I want to do something else. We've already done some work with completing the square. That's really what I want to try out here. If we wanted to set this up a little differently, maybe some of you are familiar with the vertex form, which is y minus k equals x minus h squared. And the vertex has the coordinates h for the x-coordinate and k for its y-coordinate. So this is the vertex form, and we haven't spent any time on it. I actually didn't plan to, but it occurred to me that this might be rather interesting. So I'll record it, and any of you who are interested will be watching it. Maybe that's no one. Oh well, so maybe I'm out here all by myself. We're going to use completing the square to convert this into the vertex form. First of all, I'm going to subtract 5 from both sides. So I'll have y minus 5 equals a negative x squared plus 4x. But when I'm completing the square, I always want my leading coefficient here to be a positive 1. So I'm going to factor out a negative 1. That'll leave me with x squared. Now, if I factor a negative 1 out of a positive 4x, this is going to become a negative 4x. Now I'm going to leave some space, because you know when I complete the square, I have to make a perfect square trinomial. So I have one more term that's going to go on here, and it's always going to be added. How do I figure out what it is? I take half of this and square it. Half of this would be negative 2. And I square negative 2, it gives me, that's right, positive 4. I already have the positive 4. Now, what did I just do? Effectively, I added a 4, which was multiplied by a negative 1. So that's the same as doing what? That's the same as subtracting a 4. So if I subtract a 4 from this side, by gosh, I better do it to the other side. So now I've got y minus 9 equals a negative x minus 2 squared. The whole reason that we went to a perfect square trinomial was so that we could rewrite it as a binomial squared. Well, check this out. Let me change colors. We said that our vertex would be HK, where the K would be found here and the H would be found here. So what do we see here? Our K is equal to a positive 9. Notice that it's y minus whatever K is. So y minus a positive 9. And what is my H? My H is a 2. Again, please notice it's x minus whatever H is. So that tells me that my vertex is at, let's get over here, 2, and here it is, 9. This is my vertex. Now you'll recall we figured that out a few minutes ago with what? A t-chart. The axis of symmetry, of course, is going to run right down through the center of the vertex. And if I could draw a straight line, I would. And we know because we have a negative here, whoops, off a bit, aren't I? Because we have a negative here, we're going to have the upside down version of our parent graph. So I'm going to go over 1, down 1, over 2, down 4, over 3, down 9, over 4, that would be down 16, wouldn't it? Oh, that gets a little tricky. So here's 10, 12, 14, 16. So I have this lovely parabola coming right down through here. Let's see if I can get up here and down through here. So that's just a different way of finding the vertex, and that was done by using the vertex form of a quadratic equation. It's a very lovely form, really, because it shows you what the coordinates are of the vertex. And in order to find that vertex form, we had to do an operation we're familiar with, completing the square. Okay, so that was my little bonus for you, a 8-minute bonus.